This is Learning Assessment Problem 6.2. We are shown the voltage waveform appearing across the capacitor and asked to determine the waveform of the current flowing through that capacitor. So first let's recall the capacitance voltage current relationship. We have a voltage V sub C appearing across the capacitor and the current I sub C flowing into the positive terminal of that V sub C voltage. The current as a function of time in the capacitor is given by C times the derivative of the voltage across the capacitor with respect to time. In this current problem, the voltage waveform is comprised of linear segments. Let's number these 1, 2, and 3. And we have in this table below those 3 time segments representing, for segment 1, the time interval is 0 to 2 milliseconds, and then the next time interval is 2 milliseconds to 6 milliseconds. And for t greater than 6 milliseconds, we'll assume that the indicated waveform has 0 amplitude. So we want to determine these derivatives of the voltage with respect to time, and since these are linear segments, we can just represent that as the change in voltage divided by change over that. We can represent that derivative by the change in voltage divided by the time interval. So for the first period, we have a voltage rise of 12 volts occurring in a time of 2 milliseconds, and this is equal to 6 times 10 to the third volts per second for the derivative. Over the second time interval, the voltage drops from 12 volts to 0 over a period of 4 milliseconds. So we have minus 12 volts over 4 milliseconds, and this is equal to minus 3 times 10 to the third volts per second. And over the third period, for t greater than 6 milliseconds, the indicated slope is a horizontal line with a slope of 0. And for the third period, for t greater than 6 milliseconds, the horizontal line has a slope of 0. Now we can calculate the capacitor current components for each of these time segments. For the first time period between 0 and 2 milliseconds, the capacitor current will be the C, which is 2 microfarads times 6 times 10 to the third volts per second, which gives us a current of 12 milliamps. Over the second interval, we'll have 2 microfarads for the capacitance times a minus 3 times 10 to the third volts per second, which is equal to minus 6 milliamps for the current. So it changes polarity between those 2 time periods. And over the third interval, the slope is 0, and therefore the capacitor current will be 0. So now we can proceed to plot that current waveform, and we begin over the period of 0 to 2 milliseconds with a current amplitude of 12 milliamps. Then the current drops to a negative 6 milliamps between 2 milliseconds and 6 milliseconds. After 6 milliseconds, the current falls back to a value of 0. So notice, although the applied voltage is unipolar, that is of one polarity, we have a current waveform which is bipolar in nature.